Okay, today we're going to talk about an electric field. And so when we're done here, you should be able to determine the direction on an electric field, and you should be able to calculate the electric field and the electric force. It's really, really important that you distinguish the difference between field and force. All right, so the electric field is the result of some sort of charged particle. It's very similar to the Earth's gravitational field. Okay, so there's like this area around the Earth, okay, where we can feel the gravitational pull in on the Earth. Okay, and it gets weaker as we get further out. Remember, as we got further out, the acceleration due to gravity decreased because we were further away from the Earth. And so the force we feel way out here is different than the force we feel right here on the Earth. And so the same thing happens with a charge. If I'm some other little positive charge out here, okay, so if I'm some floating out here, I am going to feel a force from this guy. And the closer I am to that guy, the more I'm going to feel that force. Further away I am, the less I'm going to feel that force. And the electric field is defined by its effect on a positive charge. Okay, we have Ben Franklin to think about that. I'll tell you about that later. So here's a positive charge. What would this positive charge do to this positive charge? They'll repel each other, correct? So it would push it away. And if I moved my positive charge over here, whoopsie, then it would push it away, and the positive charge would be pushed away again. And if I took that positive charge and I moved it to here, it would also be pushed away. And if I moved it so that it was over here, then it would be pushed away. If I move it over here, then it's going to get pushed away. And notice all these electric field lines that I've drawn here are all going away from my positive charge in the middle, because this positive charge here in the middle is going to push it away. No matter where I put this little guy here, he's going to get pushed away from this middle positive charge. So the electric field is actually produced by this guy. He's the one making the field. Just like the Earth is making the gravitational field that pulls on objects around the Earth, this little positive charge is making an electric field that affects this guy here. If we had a little negative charge and we did the same thing and we put that positive test charge out here, that positive test charge is now going to get sucked in. And no matter where I put it, it's going to get sucked into that negative charge. So the electric field lines always go away from the positive and towards the negative. And they are vectors, okay? Because this is the direction of the electric force, and force is a vector, so this is a vector quantity still. So we need to take into account this is going to have vector addition. We're going to find that when we put a positive next to a negative, then the electric field lines are going to go from the positive to the negative, from the positive to the negative, from the positive to the negative. And so it's really the sum of this force and this force, and so it's going to go shum. But eventually, you know, like it's going to get so weak that this is going to go out like this. And our electric field lines will never cross each other. I know I drew them so they cross because I was being sloppy. But our electric field lines are never going to cross each other. They're always going to make closed loops. So if I was going to fix this, it would look more like this, because it's going to go from the positive, so follow the arrows, from the positive to the negative. It's going to go away from the positive. So here, we're so far away from this negative that we're not really being affected by it. So here it's just going to go away, and here they're just going to come towards the negative. Now, by definition, our electric field is our force per charge. So it's newtons per coulomb. That's the unit for electric field. Be careful, okay? You might actually want in your notes write this out as electric field, okay? And make sure you distinguish this is the field and this is the force, because there's a few things we can get this mixed up with. We could mix this up with energy, okay, because it's an E, okay, so we could mix it up with energy. We could say F and think field instead of force, so make sure this is the electric field, this is the electric force, and it's newtons per coulomb. So this is what it is by definition. It's the force per unit charge. And this charge here is the one that feels the charge. This is the one feeling the force. So this is our outside charge. It feels the force. It's the force on this little charge. So here's our positive making the field. This one makes the field. Okay. This one right here is a little Q that's out here feeling the field. It's the one feeling the force. This is what the force is acting on. So since we have that the field is the force divided by the charge, remember that our electric force from Coulomb's law was K Q1 Q2 over R squared, and we're going to divide that by Q. Okay, remember this Q at the bottom is the one feeling the force, so that's going to cancel with one of those. So this Q is the other charge. This Q is this guy right here, the one making the field. And so our equation becomes KQ over R squared, where this Q is the Q making the field. Okay, it's the one that is in the center. Remember, it's our center guy here. All right, we're going to have a whole bunch of equations with different forms of K, Q, and R. And it's going to be really, really important that you keep them all straight. And if you can remember how they were derived and what their basic definitions are, like the electric field is the force per unit charge, these are both equations for electric field. So they're kind of used in different situations. This is the one feeling the force, and this is the one making the force. So these Q's are not the same Q, remember that. So if you can remember how they were derived, or you can derive them yourself, it's easier to keep track of all the different equations and all the different forms of K, Q, and R, because some of them are different. So that's as far as we're going to take it today. Remember that electric field is a vector. It has a direction. It goes away from the positive and towards the negatives. And then we have two different equations for the electric field, and you want to very much distinguish between electric field and electric force. So make sure you keep those guys straight. We'll see you tomorrow. Good luck. Bye.